So once we look at the pattern here, we see the relationship between absolute and gauge pressure. And so we can come up with this equation. This equation is perfectly fine for absolute gauge pressure. We have to add on the atmosphere because the zero is offset. You know, it's just like the plus 32. You know, the plus 32 in the Fahrenheit and the Celsius is because they're offset. The zeros are offset. And so this is the exact same thing, except it's not fixed at 32. The reason it's not fixed at 32 is because of the way the gauges work. The gauges work by having on one side the atmosphere, on the other side the gas, coming up to some equilibrium. So as long as the gas and the atmosphere are the same, it reads zero. That's how the gauge works. You know, if the atmosphere is more or less, it'll shift the direction of that. And so this is the equation. You know, otherwise, if the atmospheric pressure never changed and the gauge was, or the gauge was set for it, then this would be plus 14.7. You know, and so this would be similar to the plus 32 or the plus, what was it for Kelvin? 273.15 if you want to do it that precise. Or 273. Really because of the zeros are offset. And so this equation is another algebraic equation that we've seen similar ones for in the past. So we add those two up and then we get it. This should come out 301.9. But we're only allowed 2 sig figs, so they rounded it to 3.0 times 10 squared or 300. Okay, are we good with this? 300 kilopascal. Let's move on to this. So this is just showing the behavior of volume and temperature of a gas. And so normally when we take observations, these are the, these are the observations you take in lab. So you measure the height, which is proportional pressure. So the higher the height, the greater the pressure versus the temperature. And so they probably started at room temperature here, 22 degrees. This is close to room temperature, but this is probably the temperature of the lab. 22 degrees C, it measured 75 millimeters of mercury. And then they warm it up to 50. Warm it up to 50, the pressure goes up to 82. Cool it down to 0, pressure goes to 69. 0 is an easy temperature to hit because what do we need for 0? Ice water bath. Cool it in an ice water bath. Minus 15 is a bit harder, but get it to minus 15, goes to 66. And so you can see this pattern. The higher the temperature, the greater the pressure. Now in kinetic molecular theory, that makes total sense because the higher the temperature, the faster they're moving. The faster they're moving, the more force they're going to impact the walls with. And so it makes more sense. But we want to see, you know, is this relationship linear or is this relationship non-linear? You know, like a curve. Like the density of water had a very complicated math equation. Do you remember that? The math equation is because it was a parabolic type relationship, and so it's got some kind of parabolic type equation. But let's take a look at the data. And so we look at this data here and see, is it a linear relationship or non-linear? And so the data points are shown here. We just took 4 data points. We take 4 data points here, and it looks pretty linear. So we're just going to make the assumption that it's linear all the way through. That's not always the case. Some things might look linear and turn out to be non-linear. But anyway, this turns out to be linear because if we take more data, we'd see it falls on this line. Okay, now we have a line like this. Now, what do? Well, what we do is we come up with an equation for that line. So what would the equation for this line be? Equation depends if we do it in Celsius. If we do this equation in Celsius, then what we're going to see is that the temperature is 0, temperature goes down, and then when we look here at the x-intercept, the x-intercept is important here because what does it mean if we have 0 pressure, 0 absolute pressure? It means that there's No gas. Can we have negative absolute pressure? Is that possible? No. We could have negative gauge pressure, but we cannot have negative because absolute pressure is looking at collisions. And so what does a negative collision look like? A negative collision, would it be backwards? All of a sudden the molecule's moving forward and then goes backwards? Or what does negative kinetic energy mean? Kinetic energy goes zero. Can you go into negative kinetic energy? No, there's nothing of the sort.
Would, like a vacuum though, wouldn't that be the opposite?
A vacuum would be down to zero. But what I'm asking, okay, so we're looking at pressure. Pressure goes down, 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 and then hits zero. Zero pressure means there's no collisions. No collisions means there's no gas. Can we go negative? That is, can we have ghost particles in there giving negative collisions? No, because once you're at zero. Okay, so what happens here is once we're at zero absolute pressure, we can't go negative. So this must be the coldest temperature achievable. That coldest temperature achievable is called 0 Kelvin, absolute zero. So if we do this in terms of absolute temperature, which is shown in red here, then the coldest would be zero. Because we can't go negative absolute pressure, it's impossible. This is the wrong relationship. I was doing Charles' law, it's not. Oh, sorry. This is not done. Since I was just talking about pressure, so I was thinking height in millimeters of mercury. No, this is the height of this. In other words, this is the volume. The height of this plug. This is a plug of mercury. And so this plug of mercury either increases or decreases depending on the gas sample. This is gas sample trapped in here. So if this plug decreases, then the volume contracts. If the plug rises, then the volume expands. So sorry, this millimeters is just related to the volume. It could be related to the pressure as well. But if the height goes to zero, that means there's zero volume. Can we go to negative volumes? Is that possible? No. I'm sorry? If it breaks, the smallest you're going to get is zero. I mean, you can't go negative volume because no such thing. That is, you know what? I'd like, I'm on the low sodium diet. I'd like negative 2 grams of salt on my French fries. That way I can put more salt on the burger or something like that. Is that going to work? Is there such thing as negative 2 grams of sodium of salt? No, and so that's like you're asking for negative volume. That would be like getting negative 2 grams of salt. You know? Or I'd like a negative 1 cup milkshake because I need to lose weight. You know, there's no such thing as negative grams or volume. Now, relative, yes. You know, we could have relative pressures that are negative, and we could have relative volumes that are negative, but not absolute. And so that's the difference between relative and absolute. So anyway, absolute zero, this is lowest temperature possible, and it's based on Charles' law. I mean, when we look at that trend, it goes, and so at 0 Kelvin, equivalent to minus 273.15 degrees C, or minus 459.67 Fahrenheit. Molecular motion is stopped. We talked about that. This corresponds to zero gas volume. You cannot go negative. Zero gas volume is the smallest. According to kinetic molecular theory, average kinetic energy of the substance is zero at absolute zero, so there's no kinetic energy. Even though the atoms stop moving at 0 Kelvin, they're little tiny particles called electrons. And those electrons actually don't stop moving at 0 Kelvin. Those electrons continue to move. That's called the 0-point energy. And so the kinetic energy of the atoms is zero, but there's still 0-point energy residual. So this is the particulate level. You know, the higher the temperature, the more forceful the collision. And so here we have atmospheric pressure pushing outside and the gas pressure pushing inside. The gas is more forceful, it's going to push the plug up. But this one you don't really have to worry too much understanding this at the particulate level, because there are other ways we understand. Well, that mathematics this is called Charles' law. Charles' law, we can derive the equation for that straight line, and but the mathematics involved is the volume is directly proportional to temperature. If we double the temperature, the volume doubles. If we triple the temperature, the volume triples. If we cut the temperature in half, the volume gets cut in half. So this is directly proportional. If we wanted to actually calculate it, there's a constant, you know, because temperature is Kelvin, volume is milliliters or cubic meters or whatever volume you want. Liters is most common for gases. And so this is a constant, and then we rearrange it. So this is a constant which is equal to B over T. So the ratio of volume to temperature is a constant. And so if we have a fixed gas sample and we change one or the other, then the ratio should still be the same for a fixed amount of gas. And so we get this in mathematical form. In mathematical form, and since the ratio of volume to temperature is constant, then we can take one set and equal it to a second set. So if we double the temperature, what's going to happen to the volume? It doubles. And so we could figure it out based on one set versus the second set. And so this is Charles' law in mathematical form. V1 over T1 is equal to V2 over T2. And so those observations led to this equation here, and we use Charles' law to make predictions. And so let's do a prediction here based on Charles' law. A container with flexible walls holds a gas that is cooled from 65 to 22 degrees C with no change in pressure. So the container volume is 4.5 liters initially. What is this volume after being cooled? So when we have these gas type problems, we do this. For example, 65 degrees C, we might call that T1. And 60, that's going to go to 22 degrees C, which we'll call T2. And so when it's at 65 degrees C, V1 is 4.5 liters. And so what they're asking for is V2. What is the new volume at the colder temperature? Well, it's colder temperature, the volume should contract. Higher temperature, volume should expand. So we expect the volume to be smaller. And the way I do this is I rearrange Charles' law. I rearrange Charles' law like this. V2, let's do that. I'm going to solve that equation for V2. V2 is equal to T2 over T1 times V1. And so this is a factor here. Do you see this? T2 over T1. If the temperature increases, let's say the temperature doubles, then the volume is going to increase, perhaps double. If the temperature decreases, that is T2 smaller, this is going to be a fraction. See? And so if we do this here, this is going to be, now the problem with the temperature is this. We cannot use Celsius temperature. We must use Kelvin temperature. And so I need to convert these temperatures into Kelvin. So 65, how do I convert that into Kelvin? 273. Add 273 to it. So 65 plus 273. What did you get? 338. And then 22 plus 273. 95 Kelvin. Okay, so what's happening is the temperature is decreasing, so I end up with a fraction, 295 Kelvin over 338. And so I'm just going to have a fraction of the original volume. Do you see a fraction of the original volume here? And the original volume is 4.5 liters.
Why does that have to be in Kelvin?
It has to be in Kelvin because of the zero. Let's say we go from 0 degrees C to 22 degrees C. So this is T1, this is T2. So if we go from 0 degrees C to 22 degrees C, we plug it into this equation, will it work? If I plug in T1 at 0 degrees C, no. It would fail. That's because this equation is based on the Kelvin scale. If, however, I could use Celsius, but I'd have to have a new equation. I could use Celsius if I just redo this and make the equation for this x scale, the black one. Except it's going to be a y. It's going to be a y equals mx plus b, and I'd have to have that plus b in there, so that if I did have 0, then it would be the plus b. Well, what is the plus b? It's going to be 273.15. And so every calculation I do, it have to be y equals mx plus b. To avoid having to do that plus b part, we use the absolute Kelvin. This I do not like. Here. Do you see how they did V1 over T1? I always write it like this so we could see, what impact on the original volume. The temperature decreased, so we're going to get a fraction, so it's going to be a fraction. If the temperature increases, it's going to be a multiple. And so I like to rewrite it like this, where I have the 1s and 2s, like the temperature are the same, the other variable different. And so I don't like to write it the way they did. So here they said check the temperature. Temperature decreases, which leads to decreased volume. So anyway, they got 3.9 liters.
Will it also always be liter, like milliliter?
Oh yeah, in this one it doesn't matter what the units are. It could be gallons, it could be milliliters, it could be any unit. We don't have to convert it. Just temperature we have to convert. And so it's going to be 295 divided by 338 times 4.5. 3.92 liters, which equals 3.9 liters. That's the stuff that's missing. Do you see they say this here? Temperature fraction is less than 1. Yes, the temperature fraction is less than 1, but they didn't even show us the temperature fraction. This is the temperature fraction. It can be less than 1 if it's shrinking. It can be greater than 1 if the temperature is increasing. Are we good with Charles' law?
Yes.
This is what we're doing tomorrow in lab. We're going to do Charles' law. We're only going to take 2 measurements, and we'll go through it tomorrow. I'll show you the apparatus. There's not a figure in it here. This is Boyle's law. Boyle's law is the relationship between pressure and volume. So here's the original raw data. Is this a linear relationship or non-linear relationship? Here's a non-linear relationship. The mathematics is going to be different. But actually the math isn't bad. Let's take a look at the math for this. We don't have to worry about these graphs or anything like that. Of course we could figure things out graphically, Just like in Charles' law, we could do it graphically, but it's much nicer to do it by an equation. So if I had them plotted out, I could figure out the volume at any temperature. Take the temperature and then figure out what the volume is based on the graph. We'd have to make a graph for this particular problem, but graphing is such a hassle. It's much nicer if we have an equation that works for everything. That equation wouldn't. So we got Charles' law, then we got Boyle's law. You don't have to know the names of these because we aren't even going to bother with Charles and Boyle's law pretty soon. And so Boyle's law just looks at the volume and the pressure, and this is the end here. The end result, it was nonlinear, but it turns out that it comes up with a very simple equation. simple equation for Boyle's law is P1 V1 is equal to P2 V2. This is Boyle's law. And so we can solve for pressure or volume. You just have some kind of idea where it came from, but other than that, it's not a problem. So let's just use it. A gas sample occupies 5.18 liters. So we'll call that V1. V1, 5.18 liters. And the pressure is 776 torr. So P1 is 776 torr. Find the volume of the gas. So we're looking for V2. If the pressure is changed to 827 torrs. And so what happened to the pressure? The pressure increased. Now what is a torr? Have you heard of a torr before? A torr turns out, 1 torr is 1 millimeter of mercury. And so you could just substitute millimeters of mercury. So you know, P1 776 millimeters of mercury. P2 is 827 millimeters of mercury. A torr is shorter. It was named after Torricelli, who I think invented the barometer. So if the pressure increases, what should happen to the volume? It should decrease. We could see that in the volume fraction. Okay, if we look at the volume fraction, or not the volume fraction, the pressure fraction. So we go V2. V2 is equal to P1 over P2. This is the pressure fraction times V1. And so let's see what happens to the pressure. So P1 is 776. The units cancel. This is why we could use any units we want. And the second one, 827. However, the units must be the same. So for example, one you can't have PSI, the other you can't have torr. It doesn't cancel them. And so if you look at it, the pressure went up, which means the fraction went down, which means the volume is going to go down. And so V1 is 5.18 liters. So let's see what we calculate here. Does somebody have it? You have it? What is it? 5.86, 4.86 liters. 4.86, give me one more digit.
0.05 liters.
Okay. 4.860 liters, which rounds to 4.86 liters. Here they did it. Here they did the pressure fraction. It's good. 4.86 liters. This is good. I said we're really not going to use the Charles law. We're really not going to use Boyle's law because we are going to use instead this thing. This is called the combined gas law. The combined gas law is just combining Charles law and Boyle's law into one equation. We can do that because you know, here volume is directly proportional to temperature, but inversely proportional to pressure. And so what we come up with is this. Pressure times volume over temperature is equal to constant. And so in other words, when we combine all those, we end up with this. You don't really need to know the derivation of the combined gas law, although the derivation is easy to tell an A. But I don't bother remembering Charles' law or Boyle's law. In fact, you don't have to know which one is which, or the name, or the date, you know, that kind of stuff. All I remember is this one, P1 V1 over T1 is equal to P2 V2 over T2. I just use this one. So when we go to the last problem here, the last problem, they give us the pressure and the volume. But where's the temperature? There's no temperature here. Well, they're telling us that the temperature didn't change. If the temperature didn't change, then that means if T1 equals T2, T1 equals T2, that just cancels and that simplifies to Boyle's law. Okay, if we go to the previous problem here, the previous problem is they give us the temperatures and volumes. They give us the temperatures and volumes, what's going on with the pressure? Well, they said that no change in pressure. So if there's no change in pressure, then that means P1 and P2 are the same thing and they cancel out and we're left with Charles' law. So we can see that Charles' law and Boyle's law comes from this. But there's one more thing. Here they said that they say this. You see the amount remains constant. The amount remains constant because in Chem 1A we have an even bigger one. In Chem 1A we use this one, P1 B1 over N1 T1, where N is the amount, is equal to P2 B2 N2 T2. And so in Chem 1A you'll get problems where some of the gas leaks out. If some of the gas leaks out, then we need to know what amount of gas leaked out and how is that going to impact pressure, temperature, and volume. And so this is what we use here, where N is the amount. And so this is why they're saying amount stays constant, because that's important in Chem 1A. It's not so important here because we're just assuming all of these problems, the amount stays the same. Otherwise, they're not giving you the equation for that. All right, so let's use this equation here. A cylinder in an automobile engine has a volume of 352 cubic centimeters. So we'll just call that V1. V1 equals 352 cubic centimeters. This engine takes in air at 21 degrees C, so T1 is 21 degrees C, and 0.945 atmospheres of pressure. So P1 is 0.945 atmospheres. The compression stroke squeezes and heats the gas until the pressure is 4.95 atmospheres. So P2 is 4.95 atmospheres. And the temperature is 95 degrees C. So T2 is 95 degrees C. And so we're looking for V2. What is the final volume? That's our unknown there. First thing is we need the Kelvin temperature. So 21 plus 273 is 294 Kelvin. And then 95 plus 273. What is that? 273 plus 90, 363, yeah, 368. All right, so we're solving. So what we're going to have is we're going to have two fractions here. V2 is equal to, the first one we'll do is the pressure fraction, maybe. V2 is equal to P1 over P2. And then we'll do the temperature fraction. The temperature fraction will be T2 over T1, and then the volume, V1. Here. And so the first pressure fraction is P1 over P2. So let's see what happens. P1 over P2. Looks like it's less than 1, right? And so if we increase the pressure, the volume should decrease. Followed by the temperature fraction. The temperature fraction is T2, 368. The units cancel over 294. And so the temperature went up, and so the volume should increase. So the first fraction says the volume should decrease. The second fraction says the volume should increase. So which one wins? Well, the bigger fraction wins. And the original volume is 352 cubic centimeters. So they got the pressure fraction, the temperature fraction. So we have the first pressure fraction and then the temperature fraction. Well, the pressure fraction won, obviously, because the volume decreased quite a bit. And you can see the difference is the fraction. You know, this is a significant change in the pressure. So this should be a significant decrease compared to this is not that significant in terms of temperature increase. But these two are going to have the opposite effect. So it comes out to 84.1. But I don't like it written like that. Why? Because I want to see what digit was dropped. And so I'm going to calculate this one, 0.945 divided by 4.95 times 368 divided by 294 times 352. 84.11. 84.11 cubic centimeters, which is equal to 84.1 cubic centimeters. I want that extra step in there. So I don't bother remembering Boyle's law. I don't bother remembering Charles' law. I just remember, what was this law called? Combined gas law. And so that's all you need, the combined gas law. Okay, the last part of the chapter deals with STP. Have you heard of STP before? STP is called standard temperature and pressure. There's a standard temperature. Do you know what the standard temperature is? Standard temperature is 0 degrees C. And the standard pressure? 1 atmosphere if you're in the US, or 1 bar if you're in the rest of the world. 1 atmosphere or 1 bar. The standard temperature and pressure are used to compare different gases, you know. I memorized this. But if you look in tables, that's where you'll use it. You're supposed to memorize this as well. The volume of a sample of nitrogen gas is measured as 3.62 liters when it is at 0.843 bar and 16 degrees C. What is the STP volume of the nitrogen gas sample? The STP volume of the nitrogen gas sample. Well, okay. We have volume, we'll call V1 is equal to 3.62 liters, and then T1 is 0.843 bar, and then T1 is 16 degrees C. Okay, then the second set of conditions will be at STP. And so V2, we're trying to figure out what that is. What is P2? P2 is STP pressure. STP pressure is 1 bar. Exactly. And then T2 is going to be STP temperature. What is STP? 0 degrees C. And so basically it turns out to be a combined gas law problem where we convert this to Kelvin, and just plug it into the equation. So we look at the pressure fraction here. The pressure went up. The pressure goes up, the volume should go down. And then look at the temperature fraction. The temperature went up, temperature goes up. Or no, temperature went down. Temperature went down, volume should go down. So both of these point to volume going down. So we get 2.88 liters. That's TP. There's another one called Hamilton's law or Gay-Lussac's law. Pressure is going to be directly proportional to temperature. You know, we increase the temperature, the pressure is going to go up. And it's going to have the same type of equation as we saw before, but you know, Hamilton's law is combined into the combined gas law. When we look at the combined gas law, here's the pressure. And we can relate it to temperature as well. So it looks something like this. That's P1 V1 over T1 is equal to P2 V2 over T2. And so let's say the volume doesn't change. So let's cancel out the volume. Then this would be Hamilton's law. P1 over T1 is equal to P2 over T2. Hamilton's law. This is a very strange slide because this is the end. There's no examples. The end here for chapter 3. Or chapter 4, sorry, this is chapter 4. So this is the gases in the first part. Chapter 5, let me just take a look. Chapter 5 deals with atomic theory in the nuclear atom model. Chapter 5. So we get it, it's at the end. So instead of getting into chapter 5, which deals with atomic theory, didn't we do atomic theory already? Not really. We're going to look at atomic theory in much more detail in chapter 5. Yeah. We'll do that. Instead, since we have a little bit of time left, maybe we should do some dimensional analysis. Did you guys see this thing I posted on Piazza?
Not yet.
Dimensional analysis exercises.
Donuts.
Yeah, 7 dozen is equal to how many donuts? 84 donuts. 84. 72 sodas is equal to how many 6-pack? 12, that's good. 8 dozen drinks equals how many cases? Well, we need to know.
How many are in a case?
24 in a case. 4 cases? And so if you want some additional practice with dimensional analysis, it starts off easy and then gets hard. For example, here, 327 cubic inches is equal to how many liters? Well, that gets a little hard. You remember doing this?
Yeah.
Yes.
You know, that kind of stuff. 1 kilogram per cubic meter is equal to how many grams per milliliter? And so if you want some basic dimensional analysis problems, take a look at this, and then it gets a little harder. You can try. There are a whole bunch of conversion factors here that are really useful that you can see. Maybe these are good ones. Some of these are, I don't even bother. 1.00 liters is equal to, no, you know, I don't want to memorize a whole bunch. I'm just going to go with the bare minimum, and then is that enough to do all the calculations I need to do? So this is why I never talk about this one. So, that's about the least useful one there. But the only purpose of that one is to show you how close a chord is to a liter. Chord and liter are very similar. It's similar like the bar is to an atmosphere. You know, the bar and atmosphere are very close to one another. All right, I'm going to stop early today and then.
Are there any more requirements?
All right. Yeah. Do you have goggles?
Yeah.
Goggles and regular shoes.
Do we need our lab coats?
Huh?
Do we need our lab coats?
Do you need your lab coats? We're working with. What are we working with tomorrow? Let me see. Yeah.
We need lab coats for sure.
Well, what you want to do is you want to preview it. And let me give you a quick preview of the lab tomorrow right here. All right. Basically, when I preview the lab here, we're dealing with hot and cold water and air. The only reason I want you to wear the safety goggles is because if boiling water splashes into your eyes, or if boiling water splashes onto your feet, you know, I want you to have shoes rather than sandals, because boiling water can cause third-degree burns, potentially. But as far as gloves go, you don't really need them. A lab coat, it's not really necessary. So if you have it, bring it, because it's better to get used to it. Wearing gloves, wearing a lab coat, that kind of stuff. You want to get used to it in the lower classes, because in the upper classes, it's so busy. You don't really have time to too much sensory overload. So if you're already accustomed to it, it's better. You might as well start.